Hello all. In this lecture, we'll be demonstrating the use of long short-term memory, that is in short called as LSTM, and its architectural variants, how it can be used for sequential time data varying. So the implementations that we are going through are stacked LSTM, bidirectional LSTM, multi-layer LSTM, stateful LSTM, and residual LSTM. So in the previous lecture, we have seen the implementations of RNN towards sequential data modeling. But one of the drawback in case of recurrent neural networks is their limited memory. But in case of LSTM, there are different gate mechanisms which are used. So they have 4 different gates, namely the input gate, which is used to model the input data, the output gate, which is used to handle the output data, the forget gate, which helps in forgetting some kind of information between different layers, or the redundant information which is not required between the layers, and the candidate gate, which is helpful in creating the candidate values. So with the help of these different gates, the gradient flow will be very easier when compared to the RNN architecture. So LSTM has its own benefits when compared to RNN in handling the sequential data. So for the implementation of LSTM and its architectural variants, we are making use of the same Apple stock data, and the task is the regression, that is the time series prediction. So once again, we make use of different samples of data in order to predict the current sample. So current sample or the current values can be predicted using the previous values, or the current values can be predicted using the future values. So once again, it is sequence data modeling. So the implementation requires the initial installation and importing the necessary libraries. So we are doing the initial installation. So we are making use of the Apple stock market data. So that's why we are making use of this Yahoo Finance website, and that's why installing Y Finance. So once the installation is completed, we are importing the necessary libraries. So the libraries which are required are NumPy, which is numerical Python required for dealing with numbers or arrays, pandas required for data handling or reading the CSV file, matplotlib required for plotting of the graph, and yfinance to download the Apple stock market data. From scikit-learn pre-processing submodule, we once again import the min-max scalar. So min-max scalar or some other different types of scaling can also be done. And from sklearn library, once again we have this model underscore selection submodule. From there we are importing the train test split, which is required to split the data into training and test samples. And from TensorFlow and Keras components, we need different functions, say sequential, LSTM, dense layer, bidirectional LSTM, input, and the add functions. So all these are required for the different architectural variants that we are going to implement later. So initially loading of the data set. So we are going to download the Apple stock market data, and this data for 5 years we are going to download from the Yahoo Finance website. Let us store it in a variable called as DF. So from DF, I want only the closing price of the stock market, which is an important attribute or the feature that needs to be predicted. So therefore, I store it in a variable called as data. Now let me display the first 5 or 10 rows of the data set using the head function. So we can see the different timestamps, nothing but the date and the corresponding closing price. So closing price, once again we see that they vary in terms of hundreds or thousands or 10,000s. So this is where the necessity of scaling or normalization comes into picture. So the same thing we have seen even in the previous lecture of RNN, where we have used min-max scalar in order to bring the higher values in the range of 0 to 1. So as a part of pre-processing, we are once again using the min-max scalar, and this scalar is fit on the data that we have considered, that is the Apple stock market data. Let the window size be 30. Once again, we are using this sliding window technique in order to create sequences of data in order to predict the current value. So for that, I need to differentiate between my input data and the output data. That's why we create different list for X and Y. Now let the integer vary from window size up to the length of the scaled data. So we have seen the shape of the data set as 1226 samples, So window size is 30. So for all the values varying from 30 to 1226, we need to vary this integer I, from which we will get our x and y. So x is I minus window size is to I. So I is 30 initially. So 30 minus window size is to 30. So 0 is to 30. So 0 to 29 samples is going to give me the output y, which is I, the index I. So I is 30 here. So 0 to 29 samples is going to predict my 30th sample. The same format or the same procedure what we have followed in case of RNN. So this creation of array for x and y. So once we get this x and y, we are making use of this input and output in order to get our training as well as the test data. So training and test data consist of 4 components: x train and x train and y train, which are training data input, training data output. Similarly, test data input and test data output. So let us divide it in the ratio 80 is to 20. 80% of the data is going for training and 20% is coming for testing. And the shuffling of the data, randomly shuffling of the data is been avoided. That's why it is given as false here. Why we need to avoid the randomly selecting of the data is, otherwise the temporal dependency between the data samples will be lost, because it's a sequential data. It varies with respect to time and we need to always maintain the dependency between the data. We check for the shape of the data set: x, y, x train, x test, y train and y test. The same thing what we have seen in case of RNN also. The same data set is being used here because we need to see how exactly the same data set works under RNN as well as LSTM, or how LSTM is better compared to RNN in case of handling the sequential data. So 1226 number of samples, 30 is the window size and 1 refers to the closing price. So same thing, same x and y we have, that is to be divided into training and test. So 80% of 1226 is 980. So 20% of 1226 is 246. So window size will remain the same. Number of feature we have considered is 1 here. Only the training and the test sample varies. So once again we can see how the sequence has been created. My 0th sequence comprises of 30 different samples, 0 to 29 samples, which is going to give me my y of 0. Same way, if I consider y of 30, then again 30 different samples giving rise to the next particular sample or the next particular sequence. So for this x of 0, I need to get the value y of 0. So 0 to 29 is my number of input samples that I consider, and 30th sample would be the answer. So what is my 30th sample? It is 0.11, so which is same as this. So same thing, x of 31. So the we are considering the next 30 samples here. So for x of 31, again I would be getting y of 1. This answer would be same as the first sample what we are seeing here. Now coming to plotting of the stock market data, we can have this full series plotting. On the x-axis we can have the time as a label. On the y-axis we can have the closing price, and then we have the title as Apple stock closing price. So making use of the figure function in order to have a plot, figure size 10 inches in width and 4 inches in height. We can see how the closing price varies with respect to every year starting from 2021 to 2026. Now coming to the one input sequence, we have already seen this in case of RNN, how we have developed the sequence out of samples. So 0 to 29 samples will give us one particular sequence here, one input sequence. And same thing if I have to plot or if I have to visualize for the entire data set, then here is the full series indicated using the gray color, and then let me make use of some samples like 30 samples in order to get the 31st sample or the next sample. So the input window represented using blue color, and the target value or the data point represented using the red scatter plot. So window size is 30 here, the integer let it be equal to 100. So I am trying to plot a figure of having a full series, sliding window and the target value. So what happens in full series? I want to have a plot of all the closing prices. Let the color be light gray and let the label be full series. Now what about the sliding window? Sliding window, the range is I minus window size. So I is 100 here, window size is 30. So 100 minus 30 will be equal to 70. 70 is to 100. 70 is to 100. So 70 to 99 samples will be my window size, and 100th sample is the one which I am going to predict. So I am going to predict this 100th sample, which is the ith sample, which is the 100th sample here. So I want the values to get the sliding window. I want the values in the range. I minus window size is to 1. Let all these values come in blue color. Let me have some line width for this blue color line. Let it be equal to 2. Let the label be equal to input window. Now the target variable y, which is nothing but a scatter plot or one particular data point. So that is I here. I want it from the closing price. So from the data frame we have this closing price. So I want the values from the closing price, nothing but I, all the values of I that I mentioned. Let it be in red color. Let the size of that scatter be 100. Let the target y be labeled as target y. Then I have on the x-axis, let the label be equal to time. On the y-axis, let the label be equal to close price. Let the legend be shown here. So for full series, input window and the target variable. So let me show this graph here. Now coming to defining the utility function, so that we can make use of one function in order to have a history of all the losses of all the architectural variants saved, in order to have a comparison at the end. So we define a function called as compile and train. Let me call out all the models that I am going to build later. Let the number of epochs be equal to 10. Let the batch size be equal to 30. So once again, model training using optimizer, ADAM and MSE. As mentioned in the previous lecture, we are free to decide any optimizer or any loss functions related to regression. So we are once again making use of ADAM and mean square error here. So the model has to be fit on the training as well, on the training data, that is X train and Y train. Let the number of epochs be equal to 10, that is defined later. Let the batch size be equal to 32 and verbose equal to 1, which means that I want to display the loss values after every epoch. So in case I don't want these values to be displayed, then we can keep this verbose equal to 0. In case I want to display, then I need to have all the, in case I want to display the loss functions or the loss values after every epoch, then this verbose will be equal to 1. So at the end of every training, let me print that particular model name, it has been trained. So then, so that we have a history of all the losses with respect to every architectural variant that I am developing. So now once the data has been ready, once the data has been pre-processed, it's downloaded, pre-processed, and then creation of the sequence of data is been done. Let me go with the different variants. So the first variant is the stacked or the deep LSTM. So as a name suggests, we have to stack one LSTM over the other. So these are the hyperparameters which we have already set. Window size as 30, batch size as 32, epochs equal to 10. So the stacked LSTM is a variable in which I need to develop the architecture of LSTM. So sequential in order to add the layers linearly. So that's why I need the sequential function. Now what is the input shape? What is the input given to this LSTM architecture? The shape would be window size, that is 30, 1 here, 30, 1, and then I need to have LSTM architecture with 50 different neurons. Again, we are free to decide the number of neurons here. For simplicity, we have taken it as 50. I want to return all the sequences. That's why I keep it as true, because we need to pass on the information from one LSTM to the other LSTM, because it is stacking of two different LSTM. So LSTM ideally works like a 4-layer network, neural network, because it has 4 different gates. So 4 different neural networks working together. So now there is one LSTM on top of the other. So that's why I need to pass on the information or return the sequence or the output from one LSTM to the other. That's why I'm keeping it as true. One more LSTM with 50 different neurons, and finally at the end I have the output layer. So compiling and training of this stacked LSTM architecture that we have developed, let me call it as stacked LSTM. And I want the summary of my architecture. What are the trainable parameters there? So what are the trainable parameters? The parameters are 10,400 after in the first LSTM, in the second LSTM 20,200, and at the output layer we have 51. So put together it is 30,651. So how do we get this 10,400 as? First we have one input feature. So ideally the formula is parameters equal to input features into hidden units plus whatever comes in the hidden units, nothing but the hidden layers, into the same hidden unit, so that we get the weights present in the hidden units plus the bias of the hidden unit. Bias of the hidden unit. So the number of features what we have is 1. Hidden units we have taken 50 neurons. So this becomes 50 once again into 50 plus the bias of the hidden unit. So for every hidden neuron we have the bias. So this is 50. So this is actually 2600. But as I mentioned, there are 4 different gates in LSTM. So whenever we calculate the parameter, it should be always multiplied by 4, because we have 4 different gates. So when multiplied by 4, we get the value as 10,400. So henceforth, whatever parameter calculation we had done in case of RNN, the same thing would remain. The parameter fundamental or mathematical representation would remain the same, but we need to always multiply it by 4. So same calculation happens even here. 50, the number of features now to the second LSTM are 50. So how it varies is, in place of 1, it is now 50 into 50 plus once again 50 into 50 plus the weights associated with the 50 neurons. So that value into 4. That value into 4 is 20,200. So that's why we get the number of parameters as 20,200. And then finally 51, that is number of input features. Number of input features are 50 from the previous layer into the output feature, that is 1, because we have only one layer, plus the weight associated with that layer, that is 1. So here the calculation is this way. 50 from the 50 acts as the input to this layer into one output layer plus the bias associated with this one layer. So this is 51. So same kind of calculation holds good for all the architectural variants that we come across later. So we can see after every epochs, the values of loss is decreasing. So the model is becoming stable after every epoch. So we can also see the prediction part here, how the actual values and the predicted values are, and we can also have a plot of them. So we have the stacked LSTM making a prediction on the test values. So let me call it in a variable called as prediction. Now we have seen that the actual values what we had scaled them. We had scaled them in the values of 0 to 1. So let me inverse scale it. So therefore we do this inverse transform on this prediction variable. So we apply the same scalar here and get it in a variable called as prediction. And same thing applicable even for the actual data present in the data set. So prediction is the one which is predicted by the model. Actual y values are the one which is coming along with the data set. So same inverse transform on this y test data in order to get the actual data. So now I want to display all the values of I with respect to the prediction length. So we know that in the test data we have 246 samples. So the length of prediction would be 246. For 246 value, we have these values displayed. So we have all the actual values and the corresponding predicted values. So here we are trying to maintaining only two values after the decimal point. That's why we have this 2f here. Same thing can also be plotted, actual values and the predicted values. So we want to have a figure, plot of actual, plot of prediction. We want the label for the same. We want the x-axis to be labeled as time steps, y-axis to be labeled as values, and we also want to have the legend. So we can see the variation, how the predicted values varies from the actual values. So if I take at this point of time, so the values, the actual values and the predicted values are different. So for different time steps, the values are different. The difference between them is the error, and which can be modeled using different loss functions. Now coming to the bidirectional LSTM. So it has its own advantages when compared to a simple LSTM or a stacked LSTM. So here the data processes both in the forward as well as the backward direction. So the current values can be predicted using the past values, or the current values can be predicted even using the future values. So input shape would remain the same, window size, 1, but we are making use of the bidirectional LSTM having 50 different neurons, hidden neurons, and one output layer. So then I want to have a summary of my architecture, and I want to compile and train my bidirectional LSTM, and want to have the epoch information also. That's why we had written once for all the utility function, so that we need not repeat it once again, like how many epochs or how many batch size we want. So that is called that's why we have written this compile and the train function. So what is happening in this every layer? Let us see. Bidirectional, none, 100. Why this is 100 is because it is processing is happening in both the directions, so forward as well as backward. So 2600 was the actual calculation, if you remember, that into 4, because 4 different gates we have. So 2600 is actual parameters into the number of gates, that is 4. Since it is happening in both the directions, it is once again multiplied by 2, and that's why we have this 20,800 different parameters. When coming to the dense layer, the calculation is this will change. So we have 100 neurons to 1 plus 1 dense layer. So this is giving us 101. So once again, like the stacked LSTM, we are able to see that the loss decreases after every epoch. Coming to multi-layer LSTM. So here we have developed this multi-layer LSTM with the decreasing units. So this is once again same as stacked LSTM, because we have one LSTM on top of the other. But here the benefit is that we are trying to decrease the number of units, or we are trying to decrease the number of neurons here from 100 to 50, 50 to 25. So it is just like a filtering process from low level to high level. When we reach initial layers will get us some information or a basic information, but gradually when you decrease the number of filters, what happens is we will be able to get the actual information or the deep information. So that's why we have created this multiple LSTM layers with decreasing units. So once again the input size will remain the same. So now it is left to the user how we want to have the number of neurons, like 100 to 50 and then 50 to 25. Accordingly, the summary also appears. The number of parameters in the first LSTM would be 40,800, because it is 100 different neurons. So number of input feature is 1, but we have 100 neurons, plus in the hidden layer we have 100 into their associated weights 100, and the bias associated with every neuron. This value into 4, because the number of gates are 4. So that is totally 40,800. Now coming to the second LSTM, we have 50 different neurons. So the calculation will remain the same, that is from the previous layer, the number of features, input features are 100. So 1 becomes 100 here, but we have made use of only 50 neurons. So it is 50 plus 50 into 50 plus the 50 bias associated with this 50 layers into 4. Every time it is into 4. So that is 30,200. Likewise, we can also calculate for 25 and then the dense layer. So accordingly, the calculation goes. So total number of trainable parameters are 78,626. So this is once again becoming a deep or a complex structure, but the benefit is we can have low level to high level information gain. So once again, the epoch information, the loss is going to decrease after every epoch. That could be seen here. Now coming to the stateful LSTM. So stateful LSTM, the benefits of having the stateful LSTM is we can manually control the information flow from one hidden state to other hidden state, or from one epoch or a batch to the another batch. So that is one benefit, but one constraint in this case is we cannot have the actual length of the training data. Sometimes we will have to trim the data, because the constraint here is that the training data length should be completely divisible by the batch size. In case it is not completely divisible, then we will have to do some kind of pre-processing on that data. So let us see how exactly it works. So batch size is 32. That is the hyperparameter which we can tune. So sequential layer, once again, the input size is based on the batch size, window size and the number of features. So batch size plays an important role here, because training data should be completely divisible by batch size. So no batch can be incomplete, or batch size should be always the same. And we have this LSTM with 50 neurons. Stateful equal to true, because we want to manually control the information flow. So we have to keep it true. And finally, the output layer. Same optimizer and the loss function has been used, and we are trying to get the summary of the architecture that we have developed. So what is the new data now? What is the new training data? Training data length is equal to the actual training data length minus training data length modulus batch size. So whatever remainder that we get, so say this is 980 in our case, minus 980 modulus 32. So the remainder is 20. So 980 minus 20, which is 960. So the new training length is now 960. So this calculation we have seen even in case of RNN. Now what is X train and Y train? It is 0 to 980. So all the samples from 0 to 970, sorry, 0 to 960. So all the samples from 0 to 959 is the training data, which comprises both X as well as Y. Now, in order to store all the losses belonging to this stateful RNN, we create one empty list. The epochs in the range 10, so 0 to 9, nothing but 10 different epochs. I'm trying to fit this LSTM model on the new training length what I have, that is X train underscore S, Y train underscore S. Epochs equal to 1 because I want to pass the hidden state information from one layer to the other layer. That's why epochs equal to 1 here. Even though we mentioned initially epochs, I want the total number of epochs equal to 10. When we keep this argument equal to 1, information will pass on from one layer to the other layer. And batch size is already fixed, which is 32. Shuffling of the data is not allowed, so it is false. And verbose equal to 1 because I want the information of loss at every epoch. So we can see that the loss once again decreases after every epoch, and we are also able to calculate this parameter. So we have made use of 50 different neurons, one input feature. So the calculation is once again 2600 into 4 different gates, that is 10,400. Once again for the dense layer, the calculation remains the same, that is 50 into 1 plus 1, 50 vector size from the previous layer, from the hidden layer, into the neurons in the output layer, that is 1, plus the weight associated with that neuron, that is 1. So 50 into 1 plus 1, which will be equal to 51. So the number of trainable parameters are 10,451. Now coming to the last type, that is residual LSTM. So this is very unique when compared to all the variants that we had in case of RNN. So what we try to do here is residual information or skip information. So some of the information can be skipped and the model can directly go through the training data. What gradually we do, what is the normal procedure in case of other LSTM is a normal LSTM if you consider. It goes through the data batch wise. That's why we create a batch size, right? We try to update the weights after every batch size. So this is the concept in case of a normal LSTM. But in case of residual LSTM, information will happen or pass through every batch, as well as there is something called as skip connection. So what happens in skip connection is directly the model will be able to go through all the information present in the training data set. So when both are combined, it is the residual LSTM. So because of skip connection, nothing but the shortcut, we have the code in this way. So inputs will be input layer. The shape of the data set is once again 30,1, the window size, 1. Now we have this normal LSTM with 50 neurons. Written sequences equal to true because we need to maintain the information from one hidden state to other hidden state. So written sequences equal to true on the inputs. Also we create a shortcut. That is, shortcut means we try to give 50 neurons once again in the hidden layers, but on all the values of x, or the trainable data. Now what is this shortcut? Shortcut is LSTM with 50 neurons works on the inputs. So we have the shortcut, we have the skip connection, nothing but shortcut, as well as the batch wise information. So put together we get the residual LSTM. So at the output we have this add function which has to add both all the inputs as well as the shortcut. So the information that is got just like a normal LSTM plus the shortcut or the skip connection. So for this we need the output. So at the output we have the dense layer, that is the fully connected output layer. So how this residual LSTM works is, from TensorFlow Keras we take the component called as model, which works both on the inputs and the outputs. So the inputs and the outputs are already defined here. Let me have a summary of this and try to compile and train the residual LSTM. So we can see the summary here based on how the skip connection works. Based on that we have the number of parameters here. So skip connection, we have skipped some of the information. So the number of trainable parameters will be equal to 0. We will not able to have any parameters. So gradually when we have the proper LSTM, that is this LSTM, then we have the number of trainable parameters, 2600 into 4. Once again this is 10,400. Then in the next layer we have 20,200. Likewise it increases whenever we have this add or the shortcut, the number of trainable parameters are equal to 0. So finally at the dense layer we have this 51 different trainable parameters. So the total number of trainable parameters are 41,051. So we are able to see the loss values with respect to every epoch. So the loss values are gradually decreasing. So at last we have this training loss comparison of different variants of LSTM. Stacked LSTM, bidirectional LSTM, multi-layer with the decreasing units, residual and the stateful losses. So each are given different labels. That's why we are able to see the difference in terms of colors, and then x-axis named as epochs, y-axis named as loss. And this is the legend which is appearing, and this is the figure which is titled as LSTM architectural variants, their training losses. So coming to the stacked LSTM, the loss is very high, initial loss is very high, somewhere like 0.0175, and at epoch number 1 it is decreasing and then it is becoming stable. Coming to bidirectional LSTM indicated using orange color. Once again, the loss is very high, but from epoch 1 onwards, it is becoming natural, or it is becoming stable. Coming to the multi-layer one, again, or more or less, all these variants are starting from the same loss values. So at epoch number 1, it is becoming stable. Then we have the residual one, which is indicated using the red color. So it starts from 0.02 approximately, which is showing the highest loss when compared to all other variants. At epoch number 1, it is decreasing and gradually becoming stable. And coming to the stateful LSTM, so the loss is very less when compared to all the 4 variants, which are starting at a very high value. So, but there is lot of fluctuation, but from epoch number 4, it is becoming very stable. So, again in case of LSTM, stateful LSTM has given us a high performance, good performance, or the loss is very less. Even in case of RNN, we have seen that when we are able to manually reset the hidden state, then the stateful LSTM works the best. So this is all about LSTM, that is long short-term memory, and the demonstration of the various architectural variants of LSTM in time series forecasting. Thank you.